Hi, everybody. Good morning, if that's when you're seeing this, or good afternoon, or good evening. As you can see, it happens to be morning. I have an east-facing window here in my office, so we're going to go through the lab a little bit today and see what we've got going this weekend, or whatever, for lab, and it's going to involve refraction. So hopefully that'll be useful. We'll have a couple of fun calculations of the critical angle, and so you're going to need your lab kits, and so I hope you have that. And if you don't, well, you should get one like pretty soon. You will need your laser, which is going to come in the envelope here. So if we grab that, I have the 5 milliwatt laser. Should be glued to a popsicle stick, and it should have two ends here in which you can plug in the USB cable that can go straight into your computer. Mine's already in there. And you can hook this up. Now, this is a laser. It is low power, but that doesn't matter if you shine it in your or someone else's eye. So please exercise some caution with the laser. Don't be shining it in a place where it might reflect and come back onto you. So just please be aware of that. I'm going to take a quick look here at hooking it up. And if I hook it up this way, I'll notice that there is no laser. Okay, so if that happens to you, unplug it, flip it over, turn those leads over, and replug it in, and now you can see I've got a laser coming out. So if that happens to you, please just reverse the leads. Should work. You'll need the laser, you'll need some paper and your half sheet. Now, I'm sorry, half sheet. You'll need some sheets of paper and the half circle of acrylic. Now, the lab kit that I am using, the backing has been removed. If you have the backing still on your half circle, please leave it there. If you don't have the backing on the half circle, that's okay. We can still use it, and I'll show you how to do that. Well, in either case, we'll show you how to do that. Our goal today is to try and do two things, one of which is to make measurements such that we can calculate the index of refraction of the acrylic, which is the material that makes up this half circle, and then also we're going to measure the critical angle in two different ways, and we're going to compare them. And then we're going to compare that with perhaps a standardized value, all right? But more importantly, I want you to compare your two measured values and understand how to do that. So we'll be talking a little bit about uncertainty today as well. You'll need some sheets of paper, and if you look at the laser, it's going to be resting on the popsicle stick, and if I set this down on the desk, you can see that the laser is going to be emitting laser light from a point which is slightly higher up. So if I want to shoot the laser through this half circle, which I do, I'm going to need to elevate this. So I just used a stack of paper. I used several thicknesses of paper, and I put this down on the desk. I put this laser down on the desk, and then I elevated the half circle so that I have it on a sheet of paper. What I might recommend is that you tape the laser down so it stays where you put it and doesn't move, because that will be useful for as you go through to make repeated measurements. And when you have the half circle down, I'd say probably trace the edges of it out so that you know if it does get knocked, you can put it right back to where it was. Alrighty, so with that being said, let's go ahead and give a look at the setup. I'm just going to push the screen down here so you can see what I've got going. Okay, so I've got my laser over here. It's on, and you can see the laser beam coming in through here, and I'm actually going not to tape this down just because I don't have tape handy, but you should. the laser beam's coming in here, and it's not making it quite all the way, which means it's tipped a little bit, so I'm going to push the back end of it down, and now here is where the laser is. So if I'm looking at this pretty closely, I can actually see on the edge here, I can see where the laser spot is. I can see, and also I can just tip the laser a little bit and say, yes, this is my incident line right here. And after it leaves the half circle, there it is over there. So if I just play with it a little bit like that. So I'm also going to take the paper and just kind of turn around a little bit so that I get an incident ray here, okay, along there, a refracted ray here. Now, the rays that you're going to see the most of are going to be the ones that are outside the acrylic. I cannot see a beam inside here, which is probably why you can't see it, because I am not able to look at it while it's in the acrylic. So how do we know where it is? This is what I would suggest, just tracing out the acrylic shape here, because you will need the normal to the places where the light's coming in and out. Okay, so if I say, all right, I've got the incident beam here, so I'm going to take a couple of points along that beam just so I can have a good straight line. I have a point here, and then I have the point where it is incident into the half circle there. And if I just tip a little bit here, I'm going to find that here is the outcoming, and here is a spot on that line. So now, if I take this away, you'll be able to see that I have a pretty good representation of what happened. I can draw a straight line along here to here, and if I were good, I would have my straight edge ready, but I don't, so I will grab it. Okay, so I have my straight edge here, and I'm going to say, all right, so now I've got a straight line that came in here. That's my incident ray. Here is my refracted ray here, like so. Therefore, what was the path within the acrylic? Well, I can tell that it's just from here to there, and that's it right there. So now my job is to determine the normals to the surface here. So if I drop a normal through this boundary here, I'll be able to measure these angles. I'd have that angle there as my incident angle. I have this here as my refracted angle. And then I'm going to go here and I'm going to say, well, I'm going to take approximately a tangent. And so that's going to look about like this. I'm going to go normal to that. And that'll be the normal for this boundary here, like so. And therefore the refracted angle and the incident angle are a little harder to see because I've got them very shallow. These are very small angles. But I do have an incident angle there and a refracted angle there. Okay, so I can take a look at these angles, and I can use Snell's law to try and calculate what is the index inside the half circle. I'm going to do a couple of measurements of this. I would suggest at least 3 measurements, and try to take an average of the index that you come out with. All right, so that'll be the first part of the lab here, is determining the index of the acrylic. All right, now the second part to this has to do with the critical angle, and we're going to do the critical angle measurement in a couple of different ways. Okay, so the critical angle we're going to measure by actually trying to find the critical angle by measuring the angle at which the laser light disappears from its refraction. All right, so oops, I need to be down here. All right, so here we go. I've got, if you look carefully, I think you can see that I've got an incident ray here, and then I'm going to have a refracted ray out here. And all I've got to do is turn this so that I can see that I'm getting refraction one way or another, and the refraction is bending. So I'm going to turn this so that I'm increasing the refracted angle. So this is the refracted ray here, and I'm making it more and more parallel to the surface of the plane surface of the half circle here. All right, so as I turn it, and I turn it, and I turn it, and I turn it, and I turn, it's very close right now here. It's starting to get kind of fuzzy. And now you see, here's the reflected beam here. You see how it disappeared? There's a refracted ray here. There's a slight reflection here, but if I turn such that that refraction disappears, now it's about here, coming out. Okay, as I turn it there, I must extinguish that refracted ray. Okay, you will see this start to appear before the refracted ray is gone, as I just showed you. But in order to find the critical angle, all of the refraction has to be gone. All right, so you have to turn it such that this just disappears. All right, and even now you can kind of see that it's coming out here, but I have to keep it, oops, going the wrong way. I have to keep it going such that, oh, now it's gone. Oh, no, it isn't. It's right there. Ha! Might try this with the lights out so you can really see. Yep, there it goes. Okay, so there's my reflection. And now I'd be able to do the same process. I'd be able to mark in here, here, and then mark out here, here, and then it hits right about, I can actually see inside here where it does hit. It's right about there. Okay, so yeah, I can measure the angles. When I drop a normal in here, I can measure the incident angle within the half circle and the reflected angle within the half circle. That should be my critical angle. Okay. So that's a direct measurement of the critical angle. The next thing I want you to do, okay, and so you do that the same way as we did the previous one by tracing out the shape, dotting where the line, rays are, dotting where it hits here, and then drawing it all in, moving this out of sight, and then figuring out the angles. And I do believe we have provided you a protractor in the lab kits. The second way and so do a couple of measurements of that, right? Just a couple of measurements just to see, all right, am I zoning in on the critical angle? The second method is to take the laser and vertically shine it straight in, like so. And what's fun about this is that what you'll see is, especially if you have the backing on the paper, it'll be really good if you have the backing on the paper. I mean, the backing paper on the acrylic. What you'll see, it's a little tougher in this case. So maybe if I go here, that's interesting. I found it pretty well underneath. I think maybe these are just too smooth of surfaces. There we go. Okay, so if you don't have the backing sheet on your half circle here, as I do not, then try to find a fairly, you can see I'm using the laser envelope, but try to find a fairly rough piece of paper so that you can see a circle. So what's happening here, and we'll talk about this in just a minute, but what's happening here is I'm getting a very bright center spot here. Okay, I'm getting a bright center spot. That's interesting. It looks like I'm not holding it vertically. At least to me it looks like it, but I think it's because of the camera angle. I'm getting a very bright center spot. I'm getting kind of a faded, it's hard to see. There's still light in a larger circle around this circle, and then there's a small dark ring. And then there's a little bit more light after that. All right, so I want to talk to you about how to find the critical angle from that setup. Okay, so let's take a look. The reason it's important to have a rough surface is so that when I put the acrylic on here, I'm not actually going to draw the bottom section of the acrylic. I'm just going to assume that that is it. So that if you had, for example, if you had the paper backing, that's what the back of your acrylic would look like. And then there's a thickness of the acrylic. Right? So in other words, I'm looking at the acrylic edge on, like this. Okay? So this is the thickness of the acrylic here. Maybe call that T. Light should be, what you're shooting for is light to be normally incident. In other words, coming straight in at a right angle here, like so. Okay? It's going to come straight in. The angle of refraction is going to be, well, the angle of incidence is 0. Therefore, the angle of refraction is 0, and it just goes straight. There's no deviation in this case. There is refraction in the sense that it slows down, but there's no deviation. So what's going to happen? The laser beam is going to shoot all the way down into here, and it's going to hit this. This is why it's important that this is a rough surface. It's going to hit this rough surface, and it's going to reflect diffusely. Right? In other words, there's going to be light beams that are going to be coming out like this as the laser light scatters off this rougher surface. Okay, so when that happens, it's gonna, some of it will come straight back up like this, right, like this. Okay, and it's gonna hit there, and you'll see a little bit of light. So you'll see a bright spot. This is the top. This is the top of the acrylic here, and so you'll see a bright spot in the very center. It should be almost like what the entire laser is, this very bright spot here. But then you'll see some light pretty faintly through about here. And then what's going to happen is you're going to see one of these rays here, I'm just going to pick this one, is coming in, but what if it comes in at the critical angle? If it comes in at the critical angle, then it reflects within here, and that means you don't see this light beam. It doesn't escape. So there's a dark spot here, but that's a dark circle because you're talking about an entire, you're talking about the entire area. Okay, so so where you find that thin dark ring, okay, it'll be there on both sides. You'll have something that goes up here like this and down there that like that, and same idea. This is your critical angle, and it's going to go that way. So the dark ring is just that. It goes all the way around. There's light, very faint, but should be there, up to this dark ring. Okay, so then you measure the diameter of that circle. Okay, measure the diameter of that circle. Half of that diameter will be the radius of the circle, and if I take this normal and I just drop it all the way down here, you see I've got a triangle here. I've got the triangle with the ray coming out. This angle is the critical angle, and then this leg of the triangle here is the same as the thickness of the acrylic. So I have a triangle in which, oh, and then this bottom part here is then half the diameter. Okay, so I have a triangle in which I can measure two of the sides. Okay, I know it's a right triangle because I put that normal perpendicular to the top and perpendicular to the bottom. So this is a right triangle, and I can now measure these two sides and then figure out what this angle is. Okay, and so that's how you can do that. Again, take a couple of measurements just to make sure that you have, that you're satisfied you're getting the numbers approximately where you want them to be. And then you can compare the measurement of and subsequent calculation of this critical angle with the one that we did previously. All right. Here's a fun offshoot question the fun offshoot question is, this is a dark ring, and you'd say, well, wait just a minute. The next beam that comes in here will be at greater than the critical angle, so it'll reflect too. So why is it just a small, thin, dark ring and not light from here to here and then all darkness from here to here? Right? There should be no light coming from here. But you will see that there is some light coming out here, and that this ring is pretty thin. So the pattern you're looking for is something like, I'll do it over here, is something like bright spot in the middle, right? You'll have a circle around that in which it's somewhat bright. There's light in here, and then you'll see this thin dark ring, and that's the boundary of this. And then you'll see some more diffuse light around it. So why, after the critical angle, why should there be light coming out here? That's like this light coming out here. Well, if I had made this, so sorry, I didn't make this to scale, I'm just realizing this. So if I were to do this properly, the thin dark ring would be out here, like that. And so that would be your bright spot. You'd have light all in here, a thin dark ring, and then light out here. Okay, sorry, I should have thought of making that copacetic with the diagram here. So why the light out here? Interesting question, but think about what's happening to these light rays. When they come out here, do they all leave? Well, they can, some of them do, but also remember that at any boundary there is some reflection. So when they go back down here, they come back down and then they diffusely reflect again. The same thing's going to happen with the critical angle, right? The critical angle beam is going to come down here, it's going to hit this thing, it's going to diffusely reflect again, right? Which means some of them are going to come straight out here, like that. And so you will see some light outside the critical angle ring out here as well as on the inside. But our focus here is, what's the diameter or / radius? Diameter is better because you have a larger measurement for the same uncertainty. Take the diameter, divide by 2, and you'll have your radius for this triangle, okay? So regarding uncertainties here, I do want you to keep a bit of track of the uncertainties, because what I want you to do is compare the angle that you're getting from this analysis to the angle you got from the previous one. And I want you to plot those and see how they compare. Okay, so how do they compare? Well, what I want you to do is draw a confidence interval. What's a confidence interval? Well, it's something that looks like this. I'm going to say I've got basically a number line here. Let's suppose that my critical angle, I'm just going to make up a number here. Suppose it's like, this is silly, but let's just say it's 10 degrees, okay? So I measured one at 10 degrees and I measured one at 12 degrees, all right? Oops, backwards too. There we go, 12 degrees. And so what I'm going to do is say, well, okay, if I have 2 spikes and I'm really confident in my 10 degree one and I'm really confident in my 12 degree one, well, then these don't overlap. So these are inconsistent results. Okay. If I'm not so confident in my 10 degree one, but I am reasonably confident in my 12 degree one, maybe the 12 degree one, you'll have something like this. And by the way, the width of this thing here is related to the uncertainty that you have that goes along with this measurement. So maybe maybe I'd say, yeah, I'm pretty sure it falls within about here to here, right? It's my value plus or minus a little bit, okay? And now I go to the 10 degree one here, I go, well, I'm really not confident with that one, so maybe this one looks a lot more like this, okay? Whereas here, my uncertainties, right? My uncertainties are such that within one standard deviation, well, this is a very unsymmetric plot here. It should go a little bit more like that, maybe. My uncertainties now start overlapping, is the point here, right? So that I'm not certain of my 10 degree result, but I'm not certain enough that maybe I could have messed it up and gotten a 12 degree result, or a 11.5 degree result, or something like that. So this would be more like a consistent situation. This is a situation where your results basically do not match. Okay? Now, Should you come up with this situation, I'm not going to be upset about it, and I don't think I'm going to grade you down for having this as your result, should this come up for you. But I do want you, in that case, to think about, well, how come I'm getting two very different results? Okay, I'm going to pop you back up so I can talk to you again. The first thing that maybe comes to mind is I should perhaps rethink how much uncertainty I have here. How uncertain am I? And I think one thing that often happens when you are starting on trying to estimate uncertainty, which is basically what I'm asking you to do, is that you don't know how to do it and you feel uncomfortable, and it's not something that you don't have any frame of reference. You don't have any place to go from, right? So I'll say this: when you make measurements the way we just done, for example, measuring the width of that circle, the width of the circle is not going to change. Okay, so repeated measurements don't have any meaning. What you want to do is take your measurements and make sure you make sure you're looking at them a couple of times, but those don't count as repeated measurements, so you can't use it as a data set. But you can look at your measuring device, the ruler, the tape measure that we give you in the lab kit, or if you have something that's better, use that. I happen to have a set of calipers at home. If you have those, go for it. You can look at that and say, well, how uncertain am I reading this measurement? So typically that's at least half of one of the hash marks. So if the tape is marked in millimeters, you could say plus or minus a half a millimeter. To be 100% sure, you'd say plus or minus 1 millimeter, because maybe it's close to this mark, but it's not quite as close to this mark. Well, it's definitely closer here than it is here, so you can always go higher with uncertainty with no big problems, okay? So you can think about, well, I know it's for sure between these two marks, just call it plus or minus 1 millimeter. What you don't want to do is have something like plus or minus 5 centimeters, where it's so large that you basically could say my measurement could be between 0 and 5 centimeters, right? So you don't want to try and measure something that's 2 millimeters and say the uncertainty is plus or minus a centimeter, okay? So please estimate your uncertainties and make them appropriate, okay? Think about the percentage of uncertainty that you have. If the radius of the circle is, say, 5 millimeters, and you say plus or minus 1, well, that's 20%. That should be plenty. If you say 5 millimeters plus or minus 4 millimeters, well, that's 80% uncertainty. So that means you're really uncertain. So I want you to think about how certain are you, and try to encompass that appropriately in the number that you choose for your uncertainties here. That all being said, please compare those two values. At the end, you'll find a way to calculate based on what is an accepted index of refraction. You'll be able to calculate what the critical angle is. However, when you are doing your calculations of the index of refraction, please use your numbers and your results. So in the lab, when I say calculate what the critical angle is using your index of refraction from part 1, please use your index of refraction from part 1 and not the accepted value, because look, these are mass-produced items, right? They're shooting for something, but they have uncertainty as to how much their index is going to be. So your measurement is probably better than a standardly quoted value for these materials. Okay, I think that is probably about it. So you've got a little bit of Snell's law, a little bit of right triangle geometry, and a little bit of uncertainty analysis. So a little bit of three-pronged attack here in the lab. Have fun, enjoy it. The labs that we're going to do this semester are going to be, hopefully, fun things to do. That is part of the goal of the lab here. And they will be done using hopefully fairly common household items in addition to some of the stuff that we ship you in the kits. Alrighty. So with that being said, I think that is a wrap on the lab today. So please be sure to have a bit of fun. Do that over the weekend. Write up, give me your results, and please submit by Monday at midnight so that we can roll into the next week starting fresh. Tuesday comes and we are going to start talking about lenses in combination and lenses with mirrors in combination. All right. So happy rest of your lab experience. Happy weekend. And I will talk to you on Tuesday. All righty. See you later, everybody.